The topic is mixed probability practice. The essential question is, can you take what you've learned about probability and use it to answer various questions? So you'll see that these examples throughout these notes, there's just kind of a mixture of different types of the probability we've covered. You'll notice that there'll be some compound events, there'll be some independent and dependent events, there'll be some counting trees involved. So it's really just a mix of everything we've covered, okay? So the first question says, if you rolled a 6-sided dice 3 times, how many possible outcomes are there? And I do want you to underline this and write it down, okay? Write down what I've written right here. Because basically they're just asking how many are in the sample space. Remember, sample space and the amount of possible outcomes, those are the same thing, okay? So it's not asking for what the combinations are, it's asking for how many combinations are there when you roll a 6-sided dice 3 times. What could you possibly land on? And one way that I've shown you to do this is to just do a counting tree. So over here on the left, I'm just going to go ahead and start a counting tree to kind of help you get a visual of what's going on here. So we'd start with start, and then you could, on that first roll, you can land on a 1, 2, 3, 4, 5, or a 6, okay? And then we're going to label that the first roll. Remember, we got to roll this thing 3 times. So let's say on that first roll you landed on 1. Well, the second roll you can land on 1 again because that's an independent event. The 1 is still there, making it independent. You land on a 2, 3, 4, 5, or 6. And you're going to see real fast that we don't have enough room for this because let's say you landed on 2 first. After 2, you can land on 1, 2, 3, 4, 5, or 6. If you land on 3 first, you can land on the second roll 1, 2, 3, 4, 5, or 6, and so on and so forth. So you'll see that right here we're going to have just a ton of possibilities so far, and that's only the second roll. Okay? Well, let's say you landed on 1 on the first roll, then you landed on 1 again on the second roll. On the third roll, you could totally land on 1 again, because this is an independent event. Or you can land on a 2, you can land on a 3, you can land on a 4, you can land on a 5, you can land on a 6. So you see from there, each one of these little guys is going to have its own branch of 6, and we don't have enough room for that. So that's just kind of a visual for you to see how big this is going to get. And then of course, that last little column would be all the possible outcomes that we would list if we want. So you can land on a 1, a 1, and a 1, so your possible outcomes would be 1, a 1, and a 1. Or you can land on a 1, and then a 2, 1, 1, and then a 2, and you'll see that all these possible outcomes, there's so many of them. Or we can also call it the sample space. So since they're not asking specifically for what they are, if they ask for what they are, you would have to list like 1, 1, and 1, 1, 1, and 2, 1, 1, and 3, and so on and so forth for all of those possibilities. But since it's only asking for how many are there, we can do it the fast way. So for the fast way, that involves what you know about exponents. So you got to think, how many possibilities are there when you roll it the first time? Well, there's 6 sides. So there's 6 possibilities, okay? And then how many times you're going to roll it? Well, you're going to roll it 3 times. Okay? So this would really be 6 to the 3rd power, which means 6 times 6 times 6. Well, 6 times 6, that's 36. And then 36 times 6 is going to give you 216 possible outcomes. That's how many there are. Or you could say the sample space has 216 possible outcomes. All right, the next question. It says, Jasmine got 11 shirts, 14 skirts, and 2 jackets. How many outfits can she make? Now again, it's not asking for, hey, what are they? It's just saying, how many can she make? So what you'd have to do is, well, for the shirts, there's 11 of them. And how many can she wear at a time? Just 1. Well, she can't just wear a shirt and that's her whole outfit. It's an and problem. She wants to wear a shirt and a skirt and a jacket. So and in probability means to multiply. And she's got 14 possibilities for skirts. She can only wear one at a time. And she's got 2 jacket possibilities, and she can only wear one at a time, okay? So anything to the first power is itself. So 11 is just 11. 14, to the first power is just 14. 2 to the first power is just 2. So 11 times 14 times 2 would give you 308 outfits. Number 3. There's a spinner with 2 equal sections, red and blue, and it's spun 3 times. It's got 2 equal sections labeled red and blue. I'm going to just go ahead and draw a sketch of that, and I want you to do that too so you can get a visual, please. So try your best to make it 2 equal sections, and they're labeled red and blue, and I'm just going to use an R and a B. And it wants to know the probability of the spinner landing on red all 3 times. Okay, so we're going to spin it 3 times, and it wants to know the probability of getting a red, and a red, and a red. Think about it. Is this an independent or a dependent event? It is an independent event because when we spin the spinner the first time, there's those same exact colors are still on the spinner. We didn't just take it away. If we would have been like, oh, you land on red, then you just take it away, and then you can't land on red anymore because you took that red away, that would be a dependent event. But since it's still there, that's called an independent event. Okay, so we want red and red and red all 3 times. One way that you can do this is by going like this, using a counting tree. So we have start. Remember, we spin it 3 times. So the first time, you can land on red or blue. And that's the first spin. I'm not going to label spin, I'm just going to put first. Let's say on the first time you land on red. Well, second time you could land on red, and if you land on red the first time, the second time you can land on blue. If you land on blue the first time, you could land on red the second time. If you land on blue the first time, you can also land on blue the second time. So that's our second spin. And let's say you land on red, and then the third time you spin, you land on red again. Or, you could land on blue. Here you can land on red or blue, red or blue, red or blue. So this right here is our third spin. Okay, this isn't even all the possible outcomes because we have to list those out, okay? And that involves just kind of tracing it. So I'm going to use a different color so I can see. So for a possible outcome, I can land on red, red, and then red. Sorry if you can't really see that. And that's what we want, okay? Or we could land on red, and then blue. Or the first time we can land on red, second time on the second spin we can land on blue, and then third spin we can land on red. Or we can go R, B, B. Or if we landed on blue the first time, we can land on red the second time and then red the third time. Or we can land on red, blue, sorry. Blue, red, blue, so it's confusing. Blue, blue, red. Or we can land on blue and blue and blue. So there are how many possible outcomes? 1, 2, 3, 4, 5, 6, 7, 8. 8 possible outcomes in the sample space. But that's not even answering the question. Because it's saying, what's the probability of spinning the spinner and landing on red all 3 times? Well, let's see where we see red, red, red. Well, it's blue, 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 red, blue, blah, blah, blah. There it is. Red, red, red. That occurs 1 out of the 8 times. Okay, another way to do this instead of doing a counting tree is just remembering what you know about and. What and means only in probability, okay? Well, what's the probability of landing on red? We ignore this. What was the probability of landing on red? Oh, it was 1 out of 2. And only in probability means to multiply. And what's the probability of landing on red? Go back to the spinner. Oh, 1 out of 2. And only in probability means to multiply. And what's probability of landing on red? 1 out of 2. Okay. So what's 1 times 1? 1 times 1 times 1. Well, that's 1. 2 times 2, that's 4. 4 times 2 is 8. Okay, so you'll see we have the same answer. 2 ways to do it. Okay? Number 4. If you land on 5 on the dice and the spinner, you win a candy bar. So you want 5 here and 5 here. What's the chance you'll win a candy bar? So again, there's 2 ways to do this. You want 5 and a 5. 5 here and 5 here. And one way you can do it is by doing a counting tree, also known as a tree diagram if you want. Or if you can quickly identify that this is an and problem, because you want 5 and a 5, you can do it the fast way, like this. So the probability of getting a 5 and a 5. Well, this is the 5 on the die, okay? So 5 on the die, well, there's only 1 5 out of the 6 possibilities. Probability of getting a 5 over here is 1 out of 6, okay? Well, the probability of getting a 5 on this spinner, look at this spinner, it looks a little weird. We got to make them equal sections, so this is a 5 and this would also be a 5. So probability of getting a 5 here is 1, 2, 3, 3 5s out of the 4 possibilities. Okay, like that. So now we just transfer that information to help us up here. Probability of getting a 5 on the die was 1/6. Remember what and means only in probability. And then probability of getting a 5 on the spinner was 3/4. So from there, because whenever you multiply fractions, you just go straight across. 1 times 3 is 3. 6 times 4 is 24. Well, go ahead and just simplify this. You can do that, or you can turn into a decimal right away to turn into a percentage. I don't care. A number that goes into both 3 and 24, to maintain this fractional form, it's 3. So 3 divided by 3 is 1. 24 divided by 3 is 8. Okay? So these are both acceptable answers. Or if I went 1 divided by 8, or 3 divided by 24, you would get this decimal. 0.125, 125 thousandths, okay? And that as a percentage would give you 12 and 5/10%. There's a 12 and 5/10% of you winning this candy bar. So for your summary, I want you to pick which problem on this page was the most challenging for you. Number 1, 2, 3, or 4. Okay, pick which one was the most challenging for you. And what will you remember from that problem that will help you solve similar problems in the future? So for example, if number 3 was the most challenging for you, what are you gathering from this number 3? What did we do in here that will help you answer similar problems in the future? Okay? Make sure you write out what your answers are to these questions. Number 5 says, how many ways can 5 people place first, second, or third in a race? So to help you with this problem, I'm going to go ahead and attach names to these 5 people in a race. And let's say that the people's names are Carter, Nick, Chantel, Serenity, and Bernice. Well, they're in a race, remember, okay? And there's only 5 of the people in the race, but we want to know how many can take first place. What are the possibilities for taking first place? So here they're starting the race. Carter can take first place. Nick could take first place. Chantel could take first place. Serenity could take first place, or Bernice could take first place. Let's pretend that Carter took first place. Well, if Carter took first place, can he take second place also? No. If Nick took first place, could he also take second place? No. What about Chantel? Could she take both first and second place? Or Serenity or Bernice, could they take first and second place? No, they can't. If that person's in first place, that's all that they can take. They can't take second or third place. So basically, you're going to eliminate them from the next 2 places, okay? So let's go back to the Carter example. Carter takes first place. Well, to take second place, you've got either Nick that can take second, Chantel could take second, Serenity or Bernice could take second place. if Nick took first place, only these 4 folks could take second place because Nick can't take second place also. So Carter could take second, Chantel could take second, Serenity could take second, or Bernice could take second place. So you'll see that after we have our first place person, for the second place person, there's only 4 possibilities. Here there were 5 possibilities of taking first place, but over here for second place, only the four remaining contestants could take second place. Well, let's pretend that Carter took first place, Nick took second place. Well, if Carter took first place and Nick took second place, could either of these 2 folks take third place? No. So who could take third place would be Chantel, Serenity, or Bernice. Okay? So you'll see now that after you designated your first place and your second place winner, those 2 options are no longer available for this third place slot. And you'll see that I started to do just a tree diagram to help me kind of sort this in my brain, but very quickly, I ran out of room. So we're going to use this kind of as a model right here. For that first place, there's only 5 possibilities, okay? There's 5 possibilities. And we've got to get a second place person. And how many are in the second place positions? There's 4. And for the third place, let's go ahead and examine this closer. There's only 3 people that could possibly take third place. Okay, once you've designated the first place and the second place. Okay, this is an and problem because you need a first place winner, a second place winner, and a third place winner. There's 5 possibilities for the first place, 4 possibilities for second place, and for third place there's 3 possibilities. Do we care about 4th place or 5th place? Nope, simply because the problem only asks about first place, second place, or third place in a race. Okay, so only 1 out of those 5 could take first place, only 1 out of those 4 could take second place, only 1 out of those 3 remaining could take third place. So 5 to the first power is just 5, 4 to the first power is just 4, 3 to the first power is just 3. And you'll see I changed it from x's to the multiplication symbol right there. These are interchangeable. But anyway, 5 times 4, that's 20. 20 times 3 is 60. So I'll end up with 60 ways. Okay? So please make sure you show your work for number 5. And please make sure you're listening to the video, because if you just write this, then I'll know you did not listen to the video, because I am explicitly telling you in this space right here, you need to show your work. Okay? You don't have to draw the whole counting tree, but you can draw this part right there. Okay? Number 6. There are 10 cards numbered 1 through 10 in a bag. If you only draw once, what's the probability of selecting 5 or 8? So see the stuff that I've underlined and boxed? I want you to do that too, because those are important keywords that can help you with similar problems in the future. So the sample space, or possible outcomes, I'm going to write them down so I can use that as a reference. There's 10 cards numbered 1 through 10, so I'm going to write 1 through 10 on here. Okay, and those are all cards. So cards are rectangles. So pretend that these are really nice looking cards, okay? Just trying to simulate this problem theoretically. Okay, if you only draw 1 time, what's the probability of selecting 5 or 8? Probability of getting a 5 or an 8. Okay, well, how many 5s are there? There's 1 out of the 10 possibilities. Or in probability means to add. Probability of getting an 8, there's only 1 out of the 10 possibilities. So look, these fractions have same denominators, so they're the same size pieces, so this would be maintain that same denominator, and just add 1 plus 1 is 2. Or you could have been like, okay, there's a 5 and an 8, there's 2 of them out of the 8 possibilities to get the 2, there's 5 and the 8, there's 2 of them out of the 10 possibilities, so it's 2 out of 10. Okay, let's simplify this fraction to, let's see, a number that goes into both 2 and 10 is 2. 2 divided by 2 is 1. 10 divided by 2 is 5. When I go 10 divided by 2 or 1 divided by 5, I get 0.2, or 2/10. And as a percentage, that would be 20%. There's a 20% chance of me getting a 5 or an 8 from the sample space of 10 cards. What's the probability of selecting a 2, 3, or a 4? Okay, well, probability of selecting a 2 is 1 out of the 10. We want to add that to this probability of selecting a 3. It's 1 out of 10 also. We want to add that to this probability of selecting a 4, which is also 1 out of 10. Or only probability means to add, okay? So 1/10 plus 1/10 plus 1/10 is 3/10. As a fraction, that's already in simplest form. So I'm going to go ahead and turn that into a decimal. So 3 divided by 10 is 3/10. Look, 3/10, 3/10. See, you know they're equal. And that would be 30% chance of selecting a 2 or a 3 or a 4. If you didn't want to do all this work, you just count them. Well, there's a 2 right there. 1, 2, 1, 3, and 1, 4. There's 3 of them out of the 10 possibilities, okay? Letter B, what's the probability of selecting a number less than 7? So I'm going to take a second right now and just remind you about inequalities. A number less than 7, so here's a number. We can use the number symbol. It's less than 7. That means this number is smaller than 7. And it does not equal 7 because it doesn't say less than or equal to. So this is a number less than 7. So let's go up here and look at numbers less than 7. Are you less than 7? No. Not less than 7. Nope, nope. Are you less than 7? Nope, I am 7. Are you less than 7? Yes. Are you? Yeah, I'm less than 7. Less than 7, less than 7, less than 7, and less than 7. There are 1, 2, 3, 4, 5, 6 possibilities of numbers that are less than 7 within the sample space. So probability of selecting a number that's less than 7, see how 7 is the bigger number, is, what was it, 6? Yeah, 6 of them out of the 10. Okay, we can simplify this fraction. Let's go ahead and divide by 2. 6 divided by 2 is 3. 10 divided by 2 is 5, and that's as far as it'll go fraction-wise. And if I go 6 divided by 10 or 3 divided by 5, I'm going to get 6/10, which as a percentage would be 60% chance. 60% chance of me getting a number less than 7 from the sample space. Letter C, what's the probability of not selecting the card with the number 9 on it? So we don't want the number 9. We want anything but 9. You're 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 anything but 9. You are 9. I don't want you. You're anything but 9. So see all those ones when I've talked to my paper. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 out of the 10 possibilities that fit this criteria. So it'd be 9 out of 10. So probability of not selecting 9 is all of them, or is 9 out of 10. And as a fraction in simplest form, that's already there. So let's go ahead and divide that. 9 divided by 10 is 9/10. 9/10, 9/10, which gives you a 90% chance of not selecting 9. Now another way to do this is, well, how many total possibilities were there? Well, 10 out of 10. That's all of them. And we're going to subtract the probability of getting that 9. What's the probability of getting this 9? 1 out of 10. That's the probability of getting the 9. So 10/10 minus 1/10 is 9/10, which is the exact same answer we got there. Okay? For your summary, I want you to pick a problem from this page and reread it. So reread the problem and the work. What will you remember from that problem that will help you solve similar problems in the future? Please don't slack off on this question. Really think about your answer. Really, what are you going to remember about the problem you select that will help you answer similar problems in the future? Okay? Really think about it. In the odd-odd game, you roll the dice and spin the spinner 1 time each. If both land on odd numbers, you win money. So you're going to roll this die 1 time and spin the spinner 1 time. If you land on an odd and an odd, you're going to win money. And the first question asks us, how many total combinations are possible? So it's asking for how many are in the sample space. It's asking for how many. Okay, not what are they. Okay, how many are in the sample space? So for this first one right here, how many possibilities are there in rolling this die? Well, there's 6 possibilities. You can land on 1, 2, 3, 4, 5, or 6. And how many times are you going to roll this? 1 time. Okay. And you've got to spin this spinner. So think about, what does and mean only in probability? Only in probability does and mean to multiply. And how many possibilities are right here? Here's a little note. The spinner's got equal size sections. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 possibilities over here. And how many times are you going to spin that spinner? Well, 1 time. So 6 to the first power is just 6. 8 to the first power is just 8. So 6 times 8 is 48 possible outcomes. Another way that you can come to that answer is by drawing a tree diagram, also known as a counting tree, which I've done. And you'll see that it took me a long time. So right here, we started with star. In that first column is where you would roll the die 1 time, okay? So you roll it 1 time, you can land on a 1, 2, 3, 4, 5, or 6. Well then, for that second thing that you're supposed to do is you're supposed to spin the spinner 1 time after rolling the die. Well, let's say the first time when you rolled the die, you landed on 1 on the dice. And then on that spinner, you can land on these possibilities. And if you're like, where did these numbers come from? They came right from this board right here, or this spinner. Okay? It's not your traditional 1 through 8. It's like mixed up numbers, okay? But they're equal size sections. So if you land on a 1 on the die, you can land on 11, 12, 13, 8, 6, 9, 7, or 10 on the spinner. If you land on a 2 first on the die, you can land on these possibilities on the spinner. You know, the same possibilities, okay? After we've done that with the spinner, spinning the spinner 1 time, then that third column, because remember, we're only spinning them 1 time each, you would have the sample space. So you can land on a 1 and then an 11, that's a comma. You can land on a 1 and then a 12. You can land on a 1 on the die and then a 13 on the spinner, 1 and an 8, 1 and a 6, 1 and a 9, 1 and a 7, 1 and an 8. Then let's say you landed on 2 first on the die. Well, on the spinner, when you spin the spinner, you can land on an 11. So 2 to 11, 2 12, 2 13, 2 8, 2 6, 2 9, 2 7, 2 10, so on and so forth for each one of those possibilities. And if you count all these little guys up, you're going to end up with 48. Your sample space after rolling the die and spinner and spinning the spinner 1 time each is 48 possible outcomes. Okay, and there they are. So you can do it this way, or if you remember how to do it this way, you can do it that way and you get the same exact answer. All right, it's asking now, how many combinations are winning combinations? So I don't really remember, what do you do to win? Because that took a long time for me to do this and I don't remember the question. So in that case, you'd go back up to the problem. In the odd game, you roll the die and spin the spinner 1 time each. If both land on odd numbers, you win money, okay? How many combinations are winning combinations? So you want odd and odd. How many are odd on this? Well, let me go ahead and write the sample space for the die. So on the dice, you can land on 1, 2, 3, 4, 5, or 6. And then for the spinner sample space, we can land on an 11, 12, 13. 8, 6, 9, 7, 10. Okay, how many combinations are winning combinations? Well, on the dice, how many of them are odd? Let's see, 1, 2, 3 of them are odd. So on the dice, there's 3 of them that are odd, okay? And how many of them are odd on the spinner? 1, 2, 3, 4. 4 are odd on the spinner. Okay, so you have 12 winning combinations. Another way you can do this is, let's see how many are winning here. We want both odd and odd. So this is odd numbers. Dice is odd numbers. Spinners are odd numbers. if you're like, 4 is not an odd number, that's how many are odd in those options, okay? If you're like, well, yeah, 3 is an odd number, but how'd you get 3? Right here, there's 3 of those numbers on the dice that are odd. Okay, or I can look on here. Look for the odd odds. There's 1, 2, 3, 4. None of those, because 2 is even. 5, 6, 7, 8. None of those. 9, 10, 11, 12. And none of those, because those are all, the 6 is even. So that's 12. Okay, it's 12 winning combinations. Okay, see that? Now, what's the probability of winning? What's the chance of winning? Okay. So to win, what do you got to do? You got to get an odd and an odd. So what's the probability of winning? What's the probability of getting an odd on the dice and an odd on the spinner? Okay, well, what's the probability of getting odd on the dice? How many are odd on the dice? 1, 2, 3. 3 out of the 6. And means multiply. Sorry, I can do the dot. And probability of getting odd on the spinner, 1, 2, 3, 4. 4 out of the 1, 2, 3, 4, 5, 6, 7. 4 out of the 8. Okay, you got 2 fractions that are, you're multiplying them, so you go straight across. 3 times 4 is 12. 6 times 8 is 48. I think we can simplify that. Let's go ahead and divide by 2, divide by 2. So 6 divided by 2, 12 divided by 2 is 6. 48 divided by 2 is 24. Okay, can we go again? Yeah, let's go divide by 2 again. 6 divided by 2 is 3. 24 divided by 2 is 12. Go again. Divide by 3, divide by 3. 3 divided by 3 is 1. 12 divided by 3 is 4. 1/4. So if I go 12 divided by 48, or 6 divided by 24, or 3 divided by 12, or 1 divided by 4, you'd get 0.25, 25 hundredths, which is 25%. You have a 25% chance of winning. That's awesome. Okay, so if you're like, how did you get that with the counting tree? Remember how there were 12 winning possibilities? 12 out of how many possibilities total were there? 48. So 12 out of 48 is where we got this number. There were 12 winning on the counting tree out of the 48 possibilities from the counting tree. 12 divided by 48 gives you this, gives you that, okay? So if you played the game 180 times, so you did this game 180 times, about how many times would you expect to win? Okay? Think about this. You might see it later on. If you played the game 180 times, about how many times would you expect to win? So what's the chance of winning? What do you have to do to win? What's the probability of winning? Well, winning was getting an odd and an odd, right? Well, wasn't this the chance of winning right here? 1/4. You can take any one of these, this, or this. It's probability of winning. I'm just going to do the simplest form. And that's probability of winning. But you're going to play the game 180 times. So you're going to play it 180 times. And if you're like, why do you multiply? Well, if you think about it over here, I'm not going to do the whole entire thing, but I'm going to kind of simulate what this would look like. So the first time you play, your chance of winning was 1/4. That's the first play. And then your second play, oops, that's a weird arrow. The second time you play it, the next time you spin both of them, what's your chance of winning? Well, 1 1/4. That's the second play. And then you're going to play it third time. What's the chance of winning? Well, 1 4. And the fourth time, what's the chance of winning? 1 4. See how we would have to add 1/4 to itself 180 times? Well, since multiplication is repeated addition, we can just multiply, okay? Now this looks a little confusing to me because I have a fraction right here and it times 180. To help my life a little bit, I'm going to turn 180 into its fractional form. It's not going to change the meaning of the problem, it's just going to help my brain. So 180 over 180 divided by 1 is still 180. So I'm still going 1/4 times 180, but I'm just putting it in fractional form so I can multiply straight across so it's easy for my brain. 1 times 180 is 180. 4 times 1 is 4. 180 divided by 4 gives me 45 times. That's how many times you'd expect to win if you played this thing 180 times. Okay? That's how many times you'd expect to win. So you'd expect to win. Okay? Letter E. About how many times would you have to play in order to win 100 times? Okay. This is kind of a little bit deeper thinking. They're saying, okay, in this previous example, you'd win 45 times if you played it 180, okay? So you'd win 45 times if you played it 180 times. Here they're telling you how many times would you have to play. They want to know this thing. They want to know how many times would you have to play if you want to win 100 times. So I'm going to just copy this right here. That's the chance of winning. 1/4. It's a probability of winning, you know, getting odd. And we're going to multiply it by our number of plays. Do we know our number of plays? Well, no, because it's asking how many times would you have to play. I'm going to assign a variable to that. Okay, that's the number of plays. Number of plays. We don't know it. Okay, but we know we're going to win 100 times. Okay, now all you got to do is build it to solve for x. Okay, so we started with x. Then what did we do? Oh, we multiplied it by 1/4. And what's the inverse operation of timesing by 1/4? Well, that's dividing by 1/4. So we're going to divide both sides of that equal sign by 1/4. 1/4 divided by 1/4 is 1. 100 divided by 1/4. Well, I'm not going to use a calculator because we can go ahead and do the keep, change, flip like you've learned previously, okay? So I got to go 100 divided by 1/4. 100 divided by 1/4. So let's do keep, change, flip. So we're going to keep it, change that to multiplication, and then flip this. Give me the reciprocal of 1/4, which is 4/1. Oh, I'm going to turn 100 into its fractional form so I can multiply straight across. 100 times 4 is 400. 1 times 1 is 1. 400 divided by 1 is 400. So x, which represented the number of plays, what? We'd have to play 400 times. You'd have to play 400 times to win 100. I'm sorry, to win 100 times, okay? Okay, and that kind of makes sense because your chance of winning was 1/4. So 1/4 of 400 is 100. Okay, think about that. Let that sink in for a second, okay? This table shows outcomes of a number cube with 6 equal sides, numbered 1, 2, 3, 4, 5, and 6. And in analyzing the table, I'm kind of picturing in my head, all right, every time they landed on number 1, they do a tally mark. And at the end of this, they landed on side number 1 18 times. When they landed on side number 2, that was 16 times. They landed on side number 3, 19 of their total rolls. They landed on 4, 17 of their total rolls. They landed on 5, 15 of their total rolls. And 6, also 15 of their total rolls. So how many times did they roll it? Let's see, 18 plus 16 plus 19 plus 17 plus 15 plus 15. That means they rolled it 100 times. Okay, so when they rolled that dice 100 times, this is the amount of times they landed on 1. Here's how many times they landed on 2. Here's how many times they landed on 3. Here's how many times they landed on 4. Here's how many times they landed on 5. Here's how many times they landed on 6. Okay? So based on the outcomes given in this table, how many times should we expect the number cube to land on 3 if it's rolled 40 times? Okay, let's stop for a second. Let's look at the 3. Here's side 3. Now, we shouldn't say, oh, it's 3 out of 19. No, they did not roll it 19 times. They rolled it 100 times, okay? So the chance of landing on a 3, if we just, with this, we landed on 3 19 times out of the 100. Okay, take a second and just think about what just happened, okay? You probably will see one of these on an assessment in the future, okay? So we totaled all of this up. We got 100 rolls. That's how many times they rolled it. How many times did they land on a 3? Well, 19 out of the 100. How many times did they land on 3? 19 out of the 100, okay? But now they're saying, hey, we're only going to roll it 40 times. Here they rolled it 100 times. So we're going to set up our proportion. We're going to roll it 40 times instead. Okay? So how did we go from here to here? Well, one thing that you can go do is 40 divided by 100 is 0.40. So we multiplied 100 times 0.40. That's times 9. So we're going to times this side by 0.40. Okay? So 19 times 0.40. Okay, it says 7.6. Okay? So this is how many times they landed on it. They landed on 3. If they rolled it 100 times. This is how many times they landed on 3 if they rolled it 40 times. So since you can't land on 3.6 of a time, this would be approximately 8 times. Okay? So we set up a proportion right here. Originally it was out of 100, 19 out of the 100, but then we're like, oh, we only want it out of 40. So we set up our proportion here and we were like, okay, 100 times what number gives me 40? 100 times 0.4. So if we multiplied this denominator by 0.4 to get 40, we got to do the same thing to this numerator to get that, okay? Now another way you can do this is this way. What was the probability of landing on 3? Well, it was, how many times did they land on 3? They landed on it 19 times out of the 100. And how many times are we going to roll it? Oh, 40 times. So you go 19 times 40. I'm going to go ahead and put that, it's fractional form. So 19 times 40. I got 760, okay? So this would be 760 divided by 100 times, that's in fractional form, that's a 1. 100 times 1 is 100, so 760 divided by 100 gives me 7.6, which is exactly what we got right here, which would be approximately 8 times, okay? Sorry that this looks really sloppy right there. $40 number of rolls that I just put it in fractional form because it looked like this, 40 rolls, but then to make it easier, we made it into its fractional form. We want 19 times 40 to get 760. 100 times 1 would be 100, and 760 divided by 100 is 7.6, which is approximately 8 times, which is what we got here, okay? Really think about that problem. Don't just skip it because you think it's too hard. You want to do the challenging problems because those are the ones that are going to help stretch your brain, okay? Don't give up. B, how many times should we expect the number cube to land on 1 if it's rolled 12 times? Okay, so that's really similar to letter A. So I want you to go ahead and follow the procedure we did for letter A and answer this one on your own, okay? If you don't know what to do, you need to rewind the video and rewatch what I did up here, okay? If you end up with like a decimal like this, think about it. Can I land on it 0.6 times? 7.6? No, so I'm going to round it to about 8, okay? So if you get something like 2.16 or something, that would be about 2 times. All right, number 9. Michael has a fair 6-sided cube with colored faces. He rolled it 240 times and recorded the color that was facing up after each roll. His results are shown in the table. Just a little hint, I want you to really try on this one also, okay? For this problem also. Okay, so let's underline some details here. It's a fair 6-sided six-sided number cube, and that means all the sides are, the same size, and there's 6 sides to it, and there's colored faces. Rolled it 240 times, okay? So of those 240 times, he landed on red 118 times, pink 35 times, blue 87 times. So that must mean probably red, because red has more sides to it. Because look, there's 6 sides right here, but there's only 3 colors. So think about that for a second. There's 6 sides, but there's only 3 colors here. So that means that some of the sides might have more colored than some of the other sides. Okay, there's probably more red than there is pink, and there's more blue than there is pink. So pink doesn't have very many sides colored pink. So what you got to do is, let's see, he rolled it 240 times, so 118 plus 35 plus 87, when you add those together, that does equal 240 total rolls. And based on the table, what's the most likely number of sides of Michael's cube that are red? So red, well, is it just one side? Is it 2 sides, 3 sides, or 4 sides? What's the most likely? Some of you might be like, oh, it's 4 sides because that's got the most, but that's not a really good way to approach the problem. What you got to do is this. You rolled it 240 times, right? And there were 6 sides to it, so I'm going to divide it by 6. 240 divided by 6 is 40. So if each side were equally represented, they'd each land on it 40 times, okay? So that would mean right here, this guy only has one side pink, because that's closest to 40. Okay, this right here, it's about double 40, about 2 sides. Okay, let me go ahead and stop for a second. So if I went 240 divided by the 6 sides, that means if they were all equally represented, there'd be 40 side if equally represented. But they're not equally represented. This right here, this pink, there's only one side because they landed on it 35 times. And they should have landed on it 40 times, but that's close enough. Here, this is about double 40, so that's 2 sides. So this right here, this would have to be 3 sides. 3 times 40 is 120, so that's close. So see how this adds up to 6 sides? 3, 4, 5, 6 sides. Okay? Based on the table, what's the most likely number of sides of Michael's cube that are red? Well, about 3 sides. Okay, you need to reread this problem, practice it, okay? Make sure it makes sense to you. Don't just go with 4 because that's got the most. That's not a good way to look at this type of problem, okay? All right, bye.